right, now for balancing. We're going to start off with the easy ones, the single replacement redox. We've already looked at these in 4.2 briefly because it's like precipitation reactions where you'll have a spectator and things like that. First thing to do, write the unbalanced molecular equation. Balance all the atoms in the reactants and products. Write the complete ionic equation. Cross out spectators and write the net ionic equation. And then you check your atoms and you check the charge on both sides. Now, of course, these are just regular single replacement reactions. They are not taking place in acidic solution or basic solution. Those are going to follow different rules. So, a typical single replacement reaction where you have zinc and hydrochloric acid producing zinc chloride and hydrogen gas. The first thing to do, of course, is to write out the unbalanced equation. So we have zinc plus the hydrochloric acid, and that's going to give us the zinc chloride. Now, what is the normal charge on zinc? So we can write the formula correctly. Zinc is 2 plus, so we are going to need 2 chlorides to balance that out. We get that in AQ since it says it's aqueous, and then we get hydrogen gas that's going to bubble out in the end. So first step, writing it out unbalanced. The next step, of course, is to balance the atoms. And where would we need to put something in to balance our atoms? What's not balanced? H and Cl. So we're going to put a 2 there to balance that. Now that it's balanced, we can move on to writing the complete ionic equation. Complete ionic follows the same rules as the precipitation ones. You're going to separate the aqueous ones. Now we have an additional rule here from the acid-base notes. You separate the aqueous ones that are strong acids and strong bases. Remember, weak acids and weak bases you would keep together. However, in this particular reaction, hydrochloric acid happens to be one of the strong ones, so we're definitely going to separate it. So we get zinc plus 2H plus and 2Cl minus, breaking apart into its ions, like so. Zinc chloride is a soluble ionic compound, so it's also going to break apart. So we get Zn2 plus. And remember, when that particular formula unit breaks apart, you end up getting 2 chlorides out of that. So you need to balance the chlorides in front. Hydrogen is a gas, and solids, liquids, and gases stay together. You do not separate them. So once we get to this point, now you should see that there is one spectator. What is our spectator ion here? The chloride is spectating. It's in ion form on both sides, so that's the one we're ultimately going to cross out. It's not participating in the reaction at all. And then we end up rewriting what's left over. The leftovers go down here, and you put down the net ionic equation. Now, just as a double checking measure, you should go through and check to make sure that the atoms are equal and the charge is equal, because redox is all about the charge, the oxidation numbers. So over here we have 1 zinc, we have 1 zinc, we have 2 hydrogens, we have 2 hydrogens. Atoms are balanced. Now if you look at charges on the reactant side versus the product side, zinc is 0, this is +2, so that's a total of +2 on this side. Here we have +2 for this zinc and 0, so this is also a +2. The charges have to be balanced. So that's just a way of double checking to make sure it's correct. Basic single replacements here. These ones are not taking place in acidic or basic solution, because you'll notice those ones, the rules are a little bit more lengthy and it's a little bit more complicated. Okay, so as you can see, lots of rules here. As you're doing these problems, I suggest you have them out in front of you so that you can follow along and make sure you're doing everything you're supposed to. Now, instead of me reading them all out right now, we're just going to do one at a time and work through the problem. All right, starting here. Write the separate half reactions. Now, we don't really care which one's the reduction or which one's the oxidation. We can figure that out later. But we need to separate them into two half reactions. So you need to look. One of the reactants is going to go with one of the products. And I look here and I have aluminum. If I'm trying to balance aluminum, I also need something that has aluminum in it on the other side. So the one that it would pair with is this complex ion, this AlOH4 minus. We don't have to name the complex ions in AP, but they do like to throw them into problems, so you might see them. You still apply all the normal chemistry rules and concepts with them, just so you're aware. So our first half reaction is going to be the Al going to the AlOH4, like so. And then we look up here and we have the permanganate, which you saw the pretty purple solution. That is going to go over here to manganese 4 oxide. So we write that one out over here. And we have separated our two half reactions. So that is our first step, separating them out. Now that they're separate, we can start doing the other steps. Okay, we're going to balance elements, except everything except for H and O first. So I look here, I have one aluminum, check, that one's balanced. I have one manganese, check, that one's balanced. Most of the time it's 1-to-1, but there's an occasional one where you have to balance those elements first. The next thing to do is to balance oxygen, and we do this by adding water. Why are we allowed to do this? Because this is taking place in acidic solution. So guess what's present? Water is present. And also hydrogen is present if it's in acidic solution. Okay? So we're going to first deal with the waters. For our aluminum one, we have 4 oxygens on that side, right? So we need to add in how many waters?
2.
4 waters, good.
Also, do we not include the properties of like the...
No, we will put the phases of matter back at the end. You don't need to write them right now because that just becomes extra tedious. But yes, we will include the phases at the end. So I would not do it until you get to the final answer. For our permanganate going to MnO2, we need to add 2 over here to balance out the O's, because now it's a total of 4 on both sides. Okay, check, we did that one. So we did those 2. Because we added in some water, that may have adjusted our hydrogen count, so we have to balance H using H+. So if we look over here, we have 4 H's, but we have a total of 8 over here from the water we added in. So that means we should add in how many over here? 4 H+. Because we added 2 waters to the right in the permanganate equation over here, that means we also need to add in 4H+ over here to balance our H's. So check. We did that part. Now we have to balance the charge. Do not do individual elements here. It takes too long. Just go by the compound, like water, neutral, it gets a 0. Aluminum, elemental form, gets a 0. So this side is 0. AlOH4 minus, this is a -1. There's 4 H pluses, so that's a +4. So what does this one total up to? +3. Now we have to balance the charges by adding in electrons. So how many electrons do I need to add, and which side do I add them to?
3 to the right.
Yes, I add them over here. I add 3 electrons to this side. That means I have 0 equals +3 and -3, because remember, electrons are negatively charged particles, so they add in negatives. Now let's do the charge balance on this side. We have +4, -1, so this totals up to +3. This is 0 because they're neutral compounds, so this is 0. So, as you notice here, we have to add in some electrons to balance our charge. And which side would it go in? On the reactant side, and we need to add in +3 electrons. That helps balance the charge. So far, so good. So we're here now. We put in our electrons. And what you should also notice about where the electrons goes, one of them, half reaction, it went on the reactant side. The other half reaction, it went on the product side. Because remember, it is a transfer. So should be opposite sides for the half reactions. Now we get to this point here, and you'll notice that the electrons that we added in for both half reactions are the same. They're 3 and 3. That makes our life a little bit easier, because if they weren't 3 and 3, we were going to have to multiply through to get them to be the same amount of electrons. So in this particular case, this example, we don't need to multiply and do this particular step, because the electrons were already equal when we got here. Don't worry, we'll do another example where it's not the same, so you'll get to see the multiplying step. Now once we've done this, we get to the canceling and merging. Now you can do this one of 2 ways. You can merge first and then cancel, or you can cancel and then merge. Doesn't matter to me. So here, I merged them together first. I took everything that was on the reactant side of both half reactions and put them together. I took everything that was on the product side of both half reactions and put them together. So that's what you would do here to merge them. And then you can see here, we have some things that are on both sides of the reaction, and we're going to have to cancel those out. Like for instance, the first thing that's pretty obvious that you need to cancel are the electrons. 3 on the reactant side, 3 on the product side, they get canceled out. Is there anything else that we need to cancel? Hydrogen. We have 4 hydrogens on the reactant side. We have 4 hydrogens on the product side. So yes, those are going to cancel as well. And last but not least, what else do we need to cancel out? We over here on the product side, we have 2 waters. On the reactant side, we have 4. So the 2 waters on the product side completely disappear and go away. But that means we take away 2 from our original 4, and that cancels down to only 2 here on this side. And then when all is said and done, you see the cancellation process. And we end up with our final balanced inacidic solution redox reaction. And yes, at this point, this is when you would put back in the phases. So liquid for water, solid for the aluminum, aqueous for the permanganate, aqueous for the aluminum complex ion, and solid for the MnO2. That's when you would stick them back in at the end, so you're not wasting your time rewriting it over and over again. All right. Now let's look at another one. One that is going to have that multiplying stuff in it. As you can see, permanganate's in this one again, because permanganate is an oxidizer that's used a lot in redox reactions. We have permanganate plus oxalate giving us the manganese 2 ion and carbon dioxide. That's what we see up here. First up, separate into the half reactions. So let's do that. Which one is the permanganate going to go with? Has to go with Mn. Good. So that's the one we're going to put it with. So we have MnO4 going to Mn2 plus. First half reaction. That means the oxalate is going to go with carbon dioxide. It has the same elements in it, so that makes sense. C2O4 minus 2 is CO2. Now that we have our half reactions, we can start doing the rest of the process. What's the next step? Balance everything but O and H. Thank you. So let's look here. We've got Mn and Mn. 1, 1. That one's balanced. Over here, though, 2 carbons, only 1 carbon. So we need to put a 2 there. This is an example where, yes, you have to balance those first. And if you don't balance them first, then it throws off the rest of the balancing. Okay, now we can go to oxygen. Oxygen's next. So what do I need to add over here? 4 waters. Good. Because I have 4 of my oxygens over there. Look over here to the oxalate side with the carbon dioxide. We have 4 oxygens here and 4 oxygens here. Do we need to add water? No water needed to be added to that side. So that makes that a little easier. Now over on the left here, to balance our hydrogens, we need to add some hydrogens in. How many do we add? We need 8 hydrogens. Good. 8 hydrogens to balance the waters over there. All right. After we've done hydrogen, now comes charge balancing. Gotta do charge balancing. So this is plus 8. This is minus 1. So this is a total of plus 7. Good. This is plus 2. This is 0. So this is plus 2. It's a difference of 5. So we're going to need 5 electrons. Which side does it go on? Gotta go on the reactants. We add in the 5 negatives over here. We now have balanced charge. We have plus 2 on both sides.
So is the only time when elements by themselves will have a charge when it like explicitly states that it has a charge with it?
Yes. It must have a charge with it in order to be ion form, and it'd be aqueous because it'd be in solution that way. On the oxalate side, we have minus 2, we have 0. So this is difference here of minus 2. We need to add in electrons, so they're going to go where? On the right, and we need 2 of them to balance that charge. So now it's minus 2, minus 2. But you'll notice our electron count is not the same this time. So we have to multiply through to get our electrons to be equal. So over here on this side, we go with the least common multiple idea. Least common multiple between 5 and 2 is 10. So I'm going to multiply this side by 2. Multiply this side by 5. So now we're going to get 10 electrons here. We're going to get 16 hydrogens. Oh, we need 2 permanganates. So let's do that. Plus 2 permanganates. That's going to give us over here 2 magnesium 2 ions, manganese ions, excuse me. And we're going to get 8 waters. On this side, we're going to end up with 5 oxalates going to 10 CO2s. And we're going to have 10 electrons over here. Now you can do one of 2 things. You can merge and then cancel, or you can cancel and then merge. I usually at least start with getting rid of the electrons. Okay? But since the right side doesn't have water or hydrogen, we don't have to worry about canceling here. So really, in essence, all you have to do at the end here is merge these together and write in the phases. So we get 16 hydrogens. Hydrogen being positive here means it's in ion form, it's AQ. We get 2 permanganates, ions as well. And we also end up with 5 oxalates as the reactants, AQ. Now as the products, we have 2 of our manganese 2 ions. We have 8 waters. Water is pure liquid substance. And we have 10 carbon dioxides, and the carbon dioxide is gas, which it tells you up here in the original equation. And we end up with our final balanced redox reaction. Common mistake in balancing redox reactions is people go straight to just balancing the atoms and not taking into account the electrons and breaking it up into the half reactions. And then you get that particular question wrong. So, we've learned how to balance them in acidic solutions. Now we're going to add on how to balance them in basic solutions. Basic solutions follows all the same steps of acidic balancing, but adds on one thing at the end. So let's talk about those steps. Balance as if it's in acidic solution. Start there, do all the steps of acidic solution. Then in the final equation, you add hydroxide into both sides. Now the amount that you're going to add in is based on how many hydrogens there are. Now, once you add hydrogens or OHs to a hydrogen side, that's going to combine to form water. And once you've combined to form water on that side, at the end you have to recancel species and merge down. Okay? So let's look at doing one of these. Another one with permanganate in it. Look at that. Here we go. So first things first, we break it up into the half reactions. The zinc, that's pretty easy. look to balance anything besides hydrogen or oxygen. Well, we have 1 manganese to 1 manganese on the left. We have 1 zinc to 1 zinc on the right, so those are balanced. Next comes the what? The oxygens, good. So, on the left here, how many waters should I add and where should I add them to? I need to add 2 to the right side, good. Like so. No oxygen in the zinc side, so we can leave that alone. But now we have to fix the hydrogens. So where do I need to put hydrogens? On the reactants here, and how many? 4 hydrogens. Good. Next thing to do is look at charge balance. Alright, charge balance, we have +4, -1, 0, 0. So this is going to be +3, and that's going to be 0. So we need to add in 3 electrons over here to the reactant side. That works. Now we have over here, we have 0 to +2. So we need to add in 2 electrons, and they go where? They go over here to the product side, good. As you can see, we have a 3-2 thing going on with our electrons, so we do have to multiply through. Gonna multiply this side by what? That one gets multiplied by 2. This side gets multiplied by 3. So we get 3 zincs going to 3 Zn2 plus. That. Plus 6 electrons over here. This side, we get 6 electrons plus 8 hydrogens plus 2 permanganates, giving us 2 MnO2s and 4 waters, right? All is wonderful. Now we've got to merge. And as I merge, I'm just going to get rid of the electrons because we know those are canceling. So we have 8 hydrogens plus 2 permanganates plus the 3 zincs. So that takes care of all of our reactants. Over here, we have 2 MnO2, 4 waters, and our 3 zinc ions. Now, if this was an acidic solution, this is pretty much where we'd stop. But it's not an acidic solution, so we have to do the last step, where we add in the hydroxides. Now we're going to add in hydroxide number based off of how many hydrogen there are. So how many hydroxides do I need to add? 8. What I do to one side, though, have to do the other. Now this turns into what? 8 waters. Very good. So we turn our 8 hydroxides and 8 hydrogens, they merge together into 8 waters. We have a little bit more canceling to do because we can cancel down the waters. This goes, the 4 goes. Take away the 4 from the 8 and you're left with 4 waters on this side. And then you can go ahead and stick in, like this is going to give you liquid. This is AQ. This is solid. This is solid. AQ, AQ. And it cleans up nice and pretty. So this is the balancing and basic solution. You have to add in the OHs at the end based off the number of hydrogens in your reaction. Now there's a couple more practice in here. We won't have time to do them today, but you can work them on your own if you'd like. The answers are in the PowerPoint, so you could check them. There's also a fun challenge problem on the back where the coefficients get quite high, and you can check that one if you'd like to do it.